Okay, so today we're really diving deep into this paper. ReCamMaster, camera-controlled generative rendering from a single video.
It's a mouthful.
It is a mouthful.
Yeah.
But super interesting stuff.
Right.
So basically what this paper is talking about is this new framework they've developed.
Okay.
And it can take a single video, like, something you shot on your phone or whatever.
Right.
And it can re-render that video with completely new camera movements.
Wow.
And you can imagine, like, the possibilities for that are pretty huge.
That's pretty crazy. I mean, how do they do that?
Yeah, so that's what we're going to get into.
Okay.
But just at the very high level.
Okay.
They're using this very interesting new video conditioning method.
Okay.
For these pre-trained text-to-video AI models that are out there these days.
Right.
And they actually created a massive custom-built training data set.
That's probably important for something like this.
I would imagine so, yeah.
Yeah.
And the main thing is that, with this new system, this new framework they've developed, they're seeing that it's doing a much better job at maintaining that visual appearance.
Okay.
And that dynamic consistency, like, with the original video, than other techniques that have been tried in the past.
So it looks more realistic.
Exactly.
Okay.
And the paper gets into a lot of really interesting detail about, like, how it compares to other techniques.
Okay.
But yeah, so think about, things like video stabilization, taking that shaky video and making it nice and smooth.
Okay.
Or like targeted super resolution, so you could have this camera that zooms in on a certain area.
Okay.
And you get, much more detail there.
Interesting.
Or even like outpainting, which I think is super fascinating.
Yeah, tell me more about that.
Yeah, so outpainting is like where, you take the original video and then it's almost like it imagines what's outside of the frame.
Wow.
And it expands the frame outwards. Yeah. So all of that, just from taking that one video that you have as input.
That is amazing.
And being able to give it to this system and having it do all this magic.
Yeah, that sounds amazing.
Right.
Especially for someone like you who's, knee deep in AI research and ML engineering all the time.
Totally.
Manipulating video and doing all this stuff that's, really difficult and complex.
Yeah, definitely.
So this is right up your alley.
Yeah, this research is super relevant to, anyone who's working in this field.
It tackles that fundamental role of camera movement.
Exactly. In like visual storytelling.
Exactly.
Like how do you,
how do you get
make it feel more cinematic?
A different feel to something that's already been created.
Exactly.
Yeah.
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 It's like taking that, that raw footage.
Yeah.
And giving it like a whole new life.
Right. Yeah, exactly.
Yeah.
Totally.
And today, everything we're talking about is coming directly from this paper that the researchers wrote.
Okay.
And he did a really good job of explaining, their methodology, how they did it.
Right.
This huge data set that they put together.
Yeah, I was going to ask you about that.
Yeah. And of course,
yeah,
the results that they got.
Yeah, the good stuff.
The good stuff.
Right.
Aren't our mission here today is to really, break this down for you?
Okay.
Like, look at the core technical contributions.
Cool.
Understand, how it actually works.
Yeah.
Talk about the strengths, the limitations, of course.
Right.
And, why this research is so relevant,
Especially right now.
For people like us,
Exactly, yeah.
Doing this stuff.
It's cutting edge stuff.
Yeah. So jump in.
Yeah, let's jump into the real meat of it here.
Okay.
So the main problem that this ReCamMaster is addressing is that, we've seen a lot of progress.
Right.
In, like, AI generated video from text or from images.
But when it comes to taking an existing video and then trying to change the camera path on that video,
right,
that is much more challenging.
I can imagine. Yeah.
And the paper does a good job of explaining like why that is.
Okay.
So the main thing is that you really need to maintain that visual consistency across all the frames.
Of course.
And you got to make sure that the movement within the scene is perfectly in sync with that new camera trajectory.
Right. So it's like believable.
Exactly.
Yeah.
Yeah, because if it's not, then you're going to get this really weird, like
uncanny valley.
Yeah, it's
disjointed kind of.
Like janky movement.
Yeah.
That just takes you out of it.
Yeah, for sure. You can totally tell that something's wrong.
Yeah.
Yeah.
And the paper goes into, some of the ways that people have tried to do this before.
Okay.
And some of the shortcomings they've went into.
Okay.
So, for example, there's this method called GCD And it was pretty promising, but it was mostly trained on synthetic data.
Right.
From like, simulator environments, like,
Not the real world.
Exactly.
Yeah.
And so what happened was that it didn't really generalize well to like real world videos. It's just that classic domain gap problem.
Right. Yeah, exactly.
Like you train it on this perfect data and then you throw it out into the real world and it's like,
it doesn't know what to do.
What is this mess?
Right. Yeah. I've seen that happen many times.
Yeah.
Yeah.
And then there were other approaches like ReCapture.
Okay.
Which actually got some pretty impressive results.
Okay.
But it was super computationally expensive.
Okay.
Because it had to do this optimization process for every single video.
Okay.
So it wasn't very scalable.
Right.
Like you couldn't just like throw...
Can't do it on your phone.
Right, exactly. You couldn't just like take, millions of videos and be like...
Run it.
Do your magic.
Yeah.
It would take forever.
Right.
And then another thing that people have tried is to actually reconstruct the whole scene in 4D.
Interesting.
Right. So like,
4 dimensions.
4 dimensions.
What's...
Yeah. So it's like 3 dimensions plus time.
Oh, okay.
Right. So it's like,
Makes sense.
Trying to create this like model of the whole scene.
Gotcha.
And how it changes over time.
Okay.
Which is a really cool idea in theory.
It sounds really cool.
Right.
Yeah.
But the problem is that, robust 4D reconstruction from just a single video is a really, really hard problem.
Yeah, I can imagine.
Like we're not quite there yet.
Especially from a single video.
Exactly.
Yeah.
So all of these, limitations that people have run into with these previous approaches really highlight
why this
ReCamMaster is so novel.
So novel.
And like why it has so much potential.
Interesting.
So the main thing that's different about this is the way that they're conditioning this pre-trained text-to-video model directly on the input video.
So like using the video itself?
Exactly.
As part of the training or?
Well, as part of like, giving it the information it needs to do its thing.
Okay.
And the authors of the paper actually point out that like this idea of like directly using the video to condition these models has kind of been overlooked in current research.
Ooh, why?
Yeah, it's interesting.
Interesting.
But, makes a lot of sense because, these large generative models already have this really rich understanding of like visuals and motion.
Yeah.
And so by feeding it the video directly, it's kind of like you're giving it this head start. Yeah.
Right.
Like it already knows so much.
Yeah.
So to make this direct conditioning work really well, the researchers had to create their own data set.
Okay. Why is that?
Yeah, because there wasn't really anything out there that was good enough.
Right.
And this was not a small task.
Okay.
They had to put together this massive
data set
called multicam video.
Multicam video.
Yeah.
Okay.
And they used Unreal Engine 5 to do it.
Wow.
So, like really high quality stuff.
Cool.
And they were very deliberate about trying to make this data set mimic the intricacies of real world filmmaking.
Okay. Yeah.
So it wasn't just like, random stuff.
Right.
They were very careful about how they put it together.
Yeah, so what kind of stuff did they include?
Yeah, so the scale of this data set is pretty mind-blowing.
Okay.
They had 136,000 videos.
What?
Yeah.
That's a lot.
It's a lot of videos.
Okay.
And these videos came from over 13,000 different dynamic scenes across 40 high-fidelity 3D environments.
Wow.
Yeah.
Oh, so they really went all out.
They went all out, yeah, and they had
variety.
122,000 different camera trajectories.
Oh, that's amazing.
That they incorporated into this data set.
Wow, okay.
Yeah, so they were really trying to capture like...
all the different ways you can move a camera.
As many different like cinematic camera movements as they could.
That makes sense.
Yeah.
Yeah.
And they, it wasn't just like... random scenes.
Yeah.
They chose very specific 3D environments.
Okay.
Like they had bustling cityscapes.
Okay.
Quiet shopping malls.
Interesting.
Open countryside.
Yeah, it's a lot of different...
a whole range of different locations and settings. Yeah, and then to populate those scenes, they had 70 different character models.
Wow.
That they used.
70 different character models.
And these character models were like all different styles too.
Oh, wow.
So they had realistic ones, anime-inspired ones,
interesting,
game-like ones.
So they had like a real mix?
They had a real mix, yeah.
Wow.
And then
cool.
To animate these characters, they had about 100 different animations that they used.
Okay.
So, things like waving, dancing, cheering.
Wow.
Like really making these scenes dynamic and interesting.
So like realistic people doing realistic things.
Exactly, yeah.
Yeah.
And then the way they designed the camera trajectories was really interesting.
Okay.
So they had rules.
Rules?
Yeah, to generate different camera movements.
Right.
So they had basic pan and tilt.
Okay.
Translations along the X, Y, and Z axis. Smooth arc shots.
Okay.
More complex random trajectories, which they did through spline smoothing.
Spline smoothing.
Which makes the motion look more natural.
Okay.
And then they even included static camera positions just to have a good baseline.
Yeah, the whole spectrum.
The whole spectrum, yeah.
Wow.
And they even thought about the camera speed.
Okay.
So they had, both constant velocities and variable speeds controlled by nonlinear functions.
Interesting.
So
what's that about?
Yeah, so in real life, when you're operating a camera, you don't just move it at a constant speed all the time.
Right.
Or
you speed up, you slow down.
You speed up, you slow down.
Right.
For dramatic effect.
For dramatic effect, yeah.
Right.
Yeah. Okay.
That's true. And then they also had two common sets of camera parameters that they used.
Okay.
Which were focal length and aperture. Which, again, adds more realism to this data set.
Yeah, so they were really trying to
Yeah, they were very deliberate.
Mimic how a real camera.
Exactly. Yeah, it's like they really thought this through.
Yeah.
Like, how do we make this as realistic as possible?
Yeah, and then
so that when we train our model on it,
right,
it actually works.
It's going to perform well in the real world.
Exactly.
Yeah.
That makes sense. So this data creation process was a huge part of why ReCamMaster is so successful.
Okay, I can see that.
Yeah.
So let's get into the nitty gritty now.
Okay.
Like, how does it actually work?
All right, so let's talk about the core innovation here.
Okay.
Which is what they call frame dimension conditioning.
Frame dimension conditioning.
Yeah.
Okay.
And this is how they're able to use that existing video to guide that pre-trained text-to-video model.
Okay, so break that down for me.
Okay, so the first thing they do is they use a 3D variational autoencoder.
A 3D VAE?
Yeah, a 3D VAE.
Okay.
And that's to create these compressed latent representations.
Okay.
Of both the input video,
right,
which they call the source,
okay,
and the target video,
okay,
which is the video with those new camera movements.
The one you want.
The one you want, yeah.
Gotcha.
And so by working in this lower dimensional latent space, it's much more efficient.
Okay, that makes sense.
Right. Less data.
Less data, yeah.
To process.
And a 3D VAZ is a really good choice here.
Okay.
Because it can capture both the spatial and temporal dependencies.
Of course.
That are in video.
Right. You need both of those. You need both of those, yeah.
Yeah.
So instead of, feeding all that high dimensional pixel data into the diffusion model, they're working with this more compact representation.
Okay, that makes sense.
Which makes everything faster.
Faster, yeah.
And then comes the really interesting part.
Right.
So they take these sequences of latent representations, which are also called tokens.
Tokens.
Yeah.
Okay.
For both the source and the target video.
Okay.
And they concatenate them along the frame dimension.
Okay, so explain that like I'm 5.
Okay, so imagine you have your original video.
Okay.
And let's say it has 30 frames.
Okay, 30 frames.
30 frames. So normally you would have a sequence of 30 latent tokens.
Okay.
Right.
Representing those frames.
Representing those frames.
Yeah.
But what they're doing is they're taking the source video's 30 tokens and the target video's 30 tokens. And they're basically interleaving them or appending them.
So now you've got 60.
So now you have 60.
Okay.
So it's source frame 1, target frame 1, source frame 2, target frame 2.
Gotcha.
And so on.
Okay, so you're
So you're doubling.
Yeah, you're doubling.
The input sequence length.
Doubling the length, yeah.
Compared to a normal text-to-video generation process.
Okay, interesting.
And the really clever part is that they don't add any extra attention layers to deal with this longer input.
Wow. Okay.
They're using the existing 3D attention mechanisms that are already in the transformer-based diffusion model.
So they're just making it work with what they've got.
Exactly.
Yeah.
That's really cool. And those attention mechanisms are already designed to capture relationships, both within individual frames and across the whole sequence of frames.
Gotcha.
So by concatenating along the frame dimension, the model can learn those correlations between the source video's content and the motion of the target video.
In a really efficient way.
Yeah. It's a very elegant solution.
I like it.
Yeah.
Smart.
And the paper compares this to some other conditioning strategies.
Okay, like what?
That people have tried.
Yeah.
So there's something called channel dimension conditioning.
Channel dimension conditioning.
Yeah, where they basically stack the latent representations of the source and target videos along the channel axis.
Okay.
So kind of like adding more color channels.
Okay, I see.
And then there's view dimension conditioning.
Okay.
Which often involves adding a dedicated view attention layer.
Interesting.
To try to aggregate information from different viewpoints.
Gotcha.
But the authors argue, and their results support this, that this frame dimension conditioning is better.
Okay, why is that?
Because it allows for richer interaction and a deeper understanding of the relationships between the source and the target.
So it's like the model can really understand what's going on.
Exactly. Yeah, it could like really see how those frames relate to each other.
And how to make the movement.
Exactly.
Yeah.
Seamless.
Yeah. Okay. Okay, so we talked about how they condition the model on the video.
Right.
But now let's talk about how they actually control the camera movement.
Okay, how do they do that?
So they use something called camera pose conditioning.
Camera pose conditioning.
Yeah.
Okay.
And the interesting thing is that they only condition the model on the target camera trajectory.
Okay.
So like the new camera movements that they want, they don't try to estimate the original camera's motion.
Okay, why is that?
Yeah, so they talk about this in the paper.
Okay.
And basically it's because in the real world, accurately figuring out the camera path from any random video you give it,
it's gonna be hard.
Can be really difficult, even with like really sophisticated techniques.
Yeah, I can.
So they're just like, you know what?
Just forget about it.
We're just gonna focus on what we can control.
Just focus on the target.
Exactly.
Yeah, okay, I like that. So to feed that target camera trajectory into the model, they use a learnable camera encoder, which is basically a fully connected layer. And that encoder takes the camera trajectory, which is basically a sequence of rotation and translation matrices for each frame in the output video. And it turns that into a feature vector. That has the same dimensionality as the visual features in the transformer network. And then that camera feature is added to the visual features after the spatial attention layer in each transformer block.
Interesting.
Yeah, so it's like, it's influencing.
So it's like fine-tuning it.
Yeah, it's fine-tuning it.
Yeah.
At each step of the way.
Based on the camera.
Based on the camera movement.
Gotcha.
Yeah.
That makes sense.
And they specifically chose not to include camera intrinsics.
What does that mean?
Yeah, so camera intrinsics are things like focal length. Principal point.
And they didn't include that as a conditioning factor. Because again, they're thinking about real world applicability.
Right.
So in their training data, they had perfect control over those intrinsics.
Right.
But in the real world, you don't always know that information.
You don't know that information. So it makes sense to leave it out.
Exactly.
So it's more generalizable.
Yeah.
Cool.
So they're trying to make this model as robust as possible.
Yeah, make it work on all kinds of videos.
Exactly.
Yeah.
Okay, so we've talked about, how they built this model.
Right.
But now let's talk about how they actually trained it.
Yeah, how do they make sure it works in the real world?
Exactly. Yeah, so they have this whole section in the paper about their training strategy for enhancing generalization. So one of the key things they did was fine-tuning. So they started with this pre-trained text-to-video model. That already had all this knowledge about how to generate video.
Right. They didn't want to mess with that too much. So they only fine-tuned the parameters of the camera encoder and the 3D attention layers.
Gotcha.
Everything else they left alone. So it's like they're just kind of like
adding a little
bit on top.
A little bit on top to give it that camera control ability.
I mean, without messing up everything else it already knows.
Without messing up everything else it already knows.
Gotcha.
Yeah.
Smart.
And then they also had to deal with that gap between the synthetic training data and real world videos.
Yeah, that domain gap.
Domain gap.
Right. So to do that,
what did they do?
They added noise to the conditional video latent during training. So it's like they're making the model
more robust.
To imperfections. Yeah. So that when it sees real world data,
it's not going to freak out.
It's
seen it before.
Exactly.
Yeah.
And then this next part I thought was really clever. They talk about improving generation capability by unifying camera control tasks.
Okay, now I'm intrigued.
Yeah, so basically what they did was they took their training process and they randomly incorporated text-to-video and image-to-video generation.
Interesting.
Alongside the video-to-video task.
Okay.
So for text-to-video, they would replace all the frames of the source video with noise.
With noise?
Yeah.
Okay.
So it's like the model has to generate the video from scratch.
From scratch?
Yeah.
Based on the text?
Based on the text prompt.
Wow.
And the camera trajectory.
That's crazy.
And then for image to video, they would keep the first frame of the source video and then replace the rest of the frames with noise.
Oh.
So it's like it has to imagine.
It has to imagine.
What happens next.
Wow.
Based on that first frame.
That's cool.
And the camera movement.
Okay.
And so you would think that like adding these extra tasks would make things worse.
It would make it more confusing.
Right. But actually it made things better.
Really?
Yeah.
Wow.
It improved the model's ability to synthesize coherent objects.
Okay.
That weren't even in the original video.
So it's like it learned.
It's like it learned.
More generally.
More generally, yeah.
Yeah.
And it also made the model capable of handling all 3 tasks.
So it can do everything.
It can do everything.
Wow, that's amazing.
Yeah, so
that's so clever.
It's like a win-win.
Yeah.
Yeah.
I love that.
Okay, so we talked about, how they built the model, how they trained it.
Yeah.
Now let's talk about the results.
Okay, let's see how well it did.
All right, so they trained this ReCamMaster on their multicam video dataset for 10,000 steps.
Okay.
At a resolution of 384 by 672 pixels.
Okay.
And then they evaluated it.
Yeah.
Using a bunch of different metrics.
Okay, like what?
So to measure the accuracy of the camera movements, they used GLMAP.
GLOMAP.
Yeah, which calculates rotation and translation errors between the predicted and ground truth camera trajectories.
Makes sense.
And then to measure the temporal synchronization, they used GIM.
GIM?
Yeah.
Okay.
Which is a technique that quantifies how many pixels are consistently matched across frames.
Gotcha.
So like, is the movement in the scene matching the camera movement?
Yeah, does it look right?
Does it look right?
Yeah.
And then they also evaluated the overall quality of the generated videos.
Yeah.
So they used metrics like FID and FVD.
Oh, nice.